Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hi, Herman and Corin. So one more preparedness topic I'd love to cover at least once on this podcast is the concept of EMP. We had a sobering episode earlier, taking an unflinching look at the worst case scenario regarding the Iranian nuclear threat, namely what a nuclear strike on some area would look like in practice. And as much as it was an uncomfortable and very raw episode, I think it was a really, really valuable conversation to have, to the extent that it can be called a conversation when all I did was send in a prompt and listen to you. But the conversation between Herman and Corin, at least, was really important. And you mentioned something in that episode that I had discounted up to now, or I thought was mostly the realm of conspiracy theories, and that is the electromagnetic pulse, or EMP. And we mentioned in the context of a nuclear, if there's going to be so many bigger problems during a nuclear attack. But one of the ones that you mentioned people don't think about is that a nuclear blast would constitute an EMP event, such that emergency services everything might be degraded, not just networks like the internet, but literally everything with a computer chip would be fried, basically, like the ultimate internet or ultimate power outage event, except that all your devices are fried permanently. So there was one thing I wanted to ask in response to that, and I mentioned that we're out of the realm of anything that's in the realm of consumer preparedness, unless one likes the idea of throwing away large chunks of cash. And I'm sure there's somebody who will be happy to sell what they call EMP resistant everything. But if just looking at the mechanics of what would be needed to make it, and the idea that it wouldn't be astronomically expensive is really not very viable. So this is something that is really, really last resort. And when we're talking about contingency planning and eventualities, we're talking about the edge of the long tail here. Nevertheless, in any comprehensive preparedness strategy that the government might operate, it has all these edge cases have to be thought of and accounted for. So my question to our dear friend and colleague ChatGPT was asking about if EMP is a hypothetical threat or a potential threat. I mean, there is two directions beyond the nuclear war one. One is an actual EMP weapon. And we saw recently in the US capture of Maduro that there's no reputable confirmed evidence that the US did use an EMP, but they did use a kind of electronic weapon that President Trump called the discombobulator. He only said that it was a secret weapon which made equipment not work. So there's been various characterizations. AP described it as a pulsed energy weapon. So regardless of what it actually was in reality, it's illustrative of the idea that electronic degrading weaponries are the world as we know it, plus and the world of science fiction and what was a few years ago maybe sounded like conspiracy theories is starting to bear an uncomfortable resemblance. So this is one of those things. It's an actual thing. If a government wanted to have a last redundancy in their control and command system designed to be hardened against EMP, this was approximately my question, would they have it and could they do it? And the answer was probably yes, and almost certainly yes. It's I think actually fair to say definitely yes, because we know that in the public domain we have actual standards that the military has released, MIL-STD 188-125, for EMP resistant communications. And of course, If we're talking about an EMP resistant communications system to preserve controlling command functions during and after an EMP event, you need to have side A, side B, and a network, and all of those points need to be resistant. So that's what I'd love to chat about, Herman and Corin, this very niche world. But we're talking about how that might actually work in terms of the hardware needed to withstand something like this, because it really does exist, according to all estimates. There is not just the typical redundancy stuff you need, like power and the electricity, the whole chain, as we mentioned, physical wire, copper, optics, whatever it's being transmitted on, has to all be down to the last centimeter resistant to this potential threat vector. So let's talk about it, Herman and Corin. No topic too obscure, as we like to say. Let's talk about EMP resistance in last contingency government C2 planning. Over to you two.
Hey everyone, welcome back to my weird prompts. I am Corn, and I am sitting here in our living room in Jerusalem with my brother. It is February 21st, 2026, and the air outside is finally starting to feel like spring, even if the news cycle feels like a permanent winter.
Herman Poppleberry here. And Corn, I have to say, I have been looking forward to this one since we finished our last deep dive into nuclear strategy. It feels like the natural next step, even if it is a bit of a grim one. We spent so much time talking about the delivery systems and the geopolitical brinkmanship, but we did not really get into the nitty-gritty of what happens to the machines that are supposed to keep the world running when the sparks start flying.
It definitely is a heavy topic, but a necessary one. Today's prompt comes from Daniel, and he wants us to dig into electromagnetic pulse resistance. Specifically, he is asking about government command and control contingency planning. He wants us to look at the technical and hardware requirements, and specifically how standards like Military Standard 188-125 apply to protecting entire communications chains.
It is a fascinating area because it sits right at the intersection of high-level physics and very practical, almost old-school engineering. When most people think about EMPs, they think about science fiction movies where all the lights go out and cars stop working. But for the people designing command and control systems, it is a very specific, very measurable threat that requires some incredibly robust solutions. We are talking about protecting the very nervous system of the state.
Right, and as Daniel mentioned in his prompt, there is often this sense that EMP talk belongs to the realm of conspiracy theories or prepper subcultures. But the reality is that the military and the government have been taking this seriously for decades. You do not write a 1,000-page technical standard like Military Standard 188-125 if you think the threat is imaginary. Especially now, in 2026, with the proliferation of directed energy weapons and the increasing fragility of our microelectronics, this is more relevant than ever.
Exactly. And I think we should start by clearing up what an EMP actually is from a technical perspective, because that dictates everything about how you defend against it. When we talk about a high-altitude electromagnetic pulse, or EMP, caused by a nuclear detonation, we are really talking about three distinct phases. They are usually referred to as E1, E2, and E3. If you do not understand the three-act play of an EMP, you cannot understand the defense.
And that is where the engineering gets complicated, because each of those phases attacks electronics in a different way, right? It is not just one big wave of energy. It is a sequence of different types of interference.
Precisely. E1 is the fast component. It happens in nanoseconds. It is caused by gamma rays hitting the upper atmosphere and knocking electrons loose from oxygen and nitrogen molecules. This is called the Compton effect. Those electrons then spiral in the Earth's magnetic field, creating an incredibly intense, incredibly fast electromagnetic field. We are talking about tens of thousands of volts per meter in a fraction of a microsecond. It is too fast for traditional surge protectors to even see. By the time a standard fuse or circuit breaker tries to pop, the E1 pulse has already fried every semiconductor in the building. It literally punches holes through the microscopic junctions in your computer chips.
So that is the one that kills the microchips, the brains of the operation. If your smartphone or your server is not shielded, E1 turns it into a brick before the life in the blast even reaches the horizon.
Exactly. Then you have E2, which is the intermediate pulse. It lasts from about 1 millisecond to 1 second. E2 is actually very similar to lightning. It is caused by scattered gamma rays and neutrons hitting the atmosphere. Because it is similar to lightning, it is actually the easiest part to defend against, because we already have a lot of experience with lightning protection systems. But, and this is a big but, E2 is only a problem if your equipment survived E1. If E1 already shattered your protective circuits and fried your surge arresters, E2 just comes in and finishes the job. It is like a second punch to a boxer who is already knocked out.
And then there is E3. That is the one that reminds me of solar flares or geomagnetic storms. It is the slow burner.
Spot on. E3 is the slow component. It can last for minutes. It is caused by the nuclear blast actually distorting the Earth's magnetic field, pushing it out, and then letting it snap back. This induces massive currents in very long conductors, like power lines and long-distance telephone cables. This is what destroys the big transformers in the power grid. It is the same mechanism as the Carrington event of 1859. So, when you are looking at Military Standard 188-125, you are looking at a set of requirements designed to stop all three of those phases from reaching the sensitive equipment inside.
Okay, so let us talk about the hardware. If I am a government planner and I need to protect a command and control center, what does the actual physical building look like? Because it is not just a normal office building with some extra thick walls. I imagine it looks more like a vault.
No, not at all like a normal building. The core concept is what they call the electromagnetic pulse shield or the Faraday cage, but taken to an extreme degree. For a facility to meet Military Standard 188-125, it essentially has to be a continuous, six-sided box made of high-quality steel or copper. Every single floor, wall, and ceiling is lined with welded steel plates. We call this the NP protection volume.
And it has to be welded, right? You cannot just bolt them together or use heavy-duty tape.
Right. If you have a seam that is just bolted, there are tiny gaps. To an E1 pulse, a tiny gap is like a wide-open door. The wavelengths are so small that they can leak through any discontinuity in the shield. The standard requires at least 80 decibels of attenuation across a wide frequency range. That means the shield has to reduce the energy of the pulse by a factor of 100 million. To achieve that, the welds have to be perfect. They actually use radio frequency leak detection to check every single inch of those welds. So, you have this massive steel box, and then the real challenge begins. Because a command and control center is useless if it is a sealed box, you need air. You need power. You need data. You need people.
That is the paradox. You have to make the box perfectly sealed to energy, but perfectly open to information and life support. How do you handle those penetrations? Every hole you cut for a pipe or a wire is a potential disaster.
That is the heart of the military standard. Every single thing that goes through that steel shield is what they call a point of entry, or POE. Let us take air vents, for example. You cannot just have a hole for an HVAC duct. Instead, they use something called a waveguide beyond cutoff. It looks like a honeycomb structure made of metal. The holes are sized so that air can pass through, but the electromagnetic waves of the EMP are literally too big to pass through the tubes. They get attenuated to the point of being harmless. It is like trying to push a basketball through a straw.
That is clever. It is like a physical filter for the frequency of the pulse. What about power? You cannot exactly send power through a honeycomb. You need actual copper wires coming from the outside world.
Power is much harder. Every power line coming into the facility has to go through a massive bank of filters and surge arresters. These are not like the power strips you buy at the store. These are heavy-duty components designed to shunt the massive energy of an E1 pulse to the ground in a fraction of a microsecond. They often use a combination of metal oxide varistors and gas discharge tubes. And they have to be placed exactly at the point where the cable enters the steel shield in a specialized entry cabinet. If you have even a few inches of unprotected wire inside the shield, that wire acts as an antenna, picks up the pulse, and re-radiates it inside the protected zone. We call that the antenna effect, and it can be just as deadly as the pulse itself.
So the shield is only as good as its weakest entry point. I am curious about the communications chain Daniel mentioned. It is one thing to protect a bunker. It is another thing to protect a network that spans the globe. How do you maintain a communications link when the entire atmosphere is essentially screaming with electromagnetic noise? If you are the president or a general, you need to talk to people who are not in the room with you.
That is where the network architecture becomes critical. If you are relying on traditional copper wires between sites, you are in trouble. Those wires act as massive collectors for the E3 pulse. This is why the military has moved so heavily toward fiber optics. Glass does not conduct electricity. An electromagnetic pulse can hit a fiber optic cable all day long, and it will not induce a current. It is the ultimate EMP resistant medium.
But wait, the fiber optic cable itself is safe, but the equipment on either end still needs to be protected, right? You still have to turn that light back into electricity to run your computers.
Exactly. The transition point is the vulnerability. You have to have the fiber optic cable enter the facility through one of those waveguides beyond cutoff we talked about. Since the core of the fiber is non-conductive, it does not bring the pulse inside. But the transceivers, the hardware that turns light back into electrical signals, those have to be inside the hardened shell. This creates what we call a hardened node. The goal is to create a network of these hardened nodes connected by non-conductive bridges.
I see. So you create these islands of hardening. But what about satellite communications? That seems like a major part of modern command and control that would be incredibly vulnerable. We rely on GPS and satellite phones for everything now.
It is a massive vulnerability. Satellites are sitting ducks for the radiation effects of a high-altitude burst. Beyond just the EMP, you have the prompt radiation and the persistent radiation belts that can fry a satellite's electronics. This is known as the System-Generated Electromagnetic Pulse, or SGEMP. Hardening a satellite is incredibly expensive because every ounce of shielding costs a fortune to launch. Most military satellites, like the Advanced Extremely High Frequency or AEHF system, are hardened to a degree, but the real strategy for contingency planning is redundancy. You do not just rely on satellites. You have high-frequency radio, you have hardened terrestrial fiber, and you have airborne relay stations like the E-4B Nightwatch aircraft.
The Nightwatch. That is the Doomsday Plane, right?
Exactly. It is a modified Boeing 747 that acts as a mobile command center. It is essentially a flying military standard 188-125 facility. It is shielded against EMP, it has its own massive power generation, and it can stay airborne for days with refueling. It even has a 5-mile-long trailing wire antenna for very low-frequency communication with submarines. The idea is that even if every ground station is gone, the chain of command stays in the air.
It sounds like a massive engineering headache. I want to go back to something Daniel mentioned in his audio prompt. He talked about the capture of Maduro and the mention of a secret weapon called the discombobulator. President Trump described it as a secret weapon that made equipment not work. Now, the official line is that there is no evidence of an EMP being used, but it brings up the idea of non-nuclear EMPs or high-power microwave weapons. How do those differ from the nuclear version we've been talking about?
That is a great distinction. A nuclear EMP is an area effect weapon. You set one off in the upper atmosphere and you affect half a continent. A high-power microwave weapon, or HPM, is a directed energy weapon. It is tactical. You point it at a specific building, a specific vehicle, or a specific radar installation. It uses a burst of microwave energy to overwhelm and fry the electronic circuits inside. It does not require a nuclear blast. It uses conventional explosives or high-powered electrical capacitors to generate the pulse.
So it is a sniper rifle versus a hand grenade.
Exactly. And the engineering to defend against HPM is similar to hemp, but the frequencies can be different. HPM weapons often operate at higher frequencies, which means they can find even smaller gaps in your shielding. If your steel plates are not perfectly welded, or if your door seals are slightly worn, an HPM pulse can find its way in. In 2026, we are seeing systems like the Leonidas from Epirus, which can take out entire swarms of drones with a single microwave pulse. That is the discombobulator in action. It is not a mystery anymore, it is a standard part of the electronic warfare toolkit.
Is that what the discombobulator might have been? A directed energy weapon?
It is certainly a possibility. There has been a lot of development in what the military calls Counter-Electronics High-Power Microwave Advanced Missile Project, or CHAMP. These are missiles or drones equipped with microwave emitters that can fly over a target and pulse its electronics out of existence without blowing anything up. It is a very attractive option for modern warfare because it is non-lethal to humans but totally neutralizing to a modern military. You can take out a command center's computers without scratching the paint on the walls.
It is interesting because it changes the stakes of command and control. If you are a commander and your screen just goes blank, you do not even necessarily know you are under attack in the traditional sense. There is no explosion, no smoke, just silence. How do you even report that you have been hit if your radio is dead?
And that is why the contingency planning has to be so robust. It is not just about the hardware surviving, it is about the procedures. If the primary comms chain goes down, how do you verify it was an attack? How do you switch to the backup? Military Standard 188-125 actually requires periodic testing, where they literally hit the facility with a simulated pulse to make sure the shield is still holding. This is called pulse current injection, or PCI testing.
Wait, they actually pulse the entire building? That sounds like a major operation.
Yes. They use these massive pulse generators. They inject a simulated E1 pulse into the power lines and the data lines to see if the filters hold up. They also do shielding effectiveness tests where they use antennas to see if any energy is leaking through the walls. It is an ongoing maintenance requirement. You cannot just build it and forget it. Steel rusts, welds crack, door gaskets degrade. If you do not test it every few years, you do not have a hardened facility, you just have an expensive basement.
It is like maintaining a submarine, but for electromagnetic waves. You have to ensure the integrity of the pressure hull at all times.
That is a perfect analogy. And just like a submarine, the most vulnerable parts are the hatches. In an EMP-protected facility, the doors are incredibly complex. They have these specialized fingerstock gaskets, basically thousands of little copper teeth that create a perfect electrical connection between the door and the frame when it is closed. If one of those teeth is bent or dirty, the shield is compromised. You actually have to be very careful when you walk through those doors not to step on the threshold and damage the contact surfaces.
I am thinking about the scale of this. We are talking about massive bunkers, specialized steel, honeycomb vents, copper teeth on doors. This sounds like it costs billions of dollars. Does this level of protection exist outside of the top tier of government? Like, is the civilian power grid protected to this standard? Because if the government is safe in a bunker but the rest of us are in the dark, that is a pretty grim scenario.
Short answer, no. Long answer, it is a subject of intense debate in the halls of power. There have been several congressional commissions on the EMP threat. The consensus is usually that protecting the entire civilian grid to military standards would be prohibitively expensive. We are talking trillions of dollars. However, there are efforts to protect the most critical nodes, like the large power transformers I mentioned earlier. These things are the size of a house. They cost millions of dollars, and they have lead times of 18 to 24 months to manufacture. If you can save the transformers with specialized neutral grounding resistors or blocking capacitors, you can eventually rebuild the grid. If the transformers fry, you are looking at years of darkness.
So the command and control centers are these hardened bubbles of functionality in what might be a very dark and silent world. That brings up a deeper question about the purpose of these facilities. If the rest of the country is fried, what is the command and control system actually commanding? Is it just about managing the aftermath?
That is the dark side of continuity of government planning. The goal is to maintain the chain of command and the ability to respond to the threat. In a nuclear scenario, the command and control system is there to ensure that the second strike capability remains intact. It is about deterrence. If an adversary knows they cannot knock out your ability to retaliate with an EMP, they are less likely to try it. It is the ultimate insurance policy. Even if the lights go out in New York and Los Angeles, the silos in North Dakota still get the order to fire.
So the hardening itself is a weapon, or at least a component of a defense strategy that prevents the war from happening in the first place. It is the silent part of mad mutually assured destruction.
Exactly. It is about removing the easy win. If you have a vulnerable command and control system, you are inviting a first strike. If your system is hardened to military standard 188-125, you are telling the world that you can take the hit and keep going. It is about resilience as a form of power.
Let us talk about the data aspect of the communications chain. We have talked about the wires and the shields, but what about the data itself? Is there a way to make the information more resilient to these kinds of events? We are moving into the age of AI-driven command and control. Does an EMP affect an AI differently than a human?
That is a great question. AI models run on massive clusters of GPUs, which are incredibly sensitive to voltage fluctuations. An E1 pulse would be catastrophic for a modern data center. But there is a move toward decentralized architectures. Instead of one giant hardened facility, you have dozens of smaller ones connected by that fiber optic network we discussed. This is the philosophy behind the Joint All-Domain Command and Control, or JADC2. It is about creating a mesh network where every sensor and every shooter is a node. If one node is taken out by an HPM weapon or an EMP, the rest of the network can route around the damage.
So even if one node is taken out, the rest of the network can survive. It is the original philosophy of the internet, but applied to the most extreme survival scenarios. But what about the hardware itself? Are we stuck with silicon forever?
We might not be. We are seeing some interesting developments in hardware that is inherently more resistant to EMPs. For example, there is research into vacuum microelectronics. Think of the old vacuum tubes from the mid-20th century. They were actually much more resistant to EMPs than modern transistors because they did not rely on delicate semiconductor junctions. They were basically just metal and glass.
Wait, so we might go back to vacuum tubes for the most critical systems. That feels like going back to the Stone Age to survive the Space Age.
Not the giant glass tubes of the past, but microscopic versions of them etched onto silicon. They are called vacuum field emission transistors. They combine the speed of modern chips with the physical robustness of a vacuum. It is still in the research phase, but it shows that we are looking for ways to build resilience into the atoms of the hardware, not just the walls of the building. We are also looking at wide bandgap semiconductors like gallium nitride and silicon carbide, which can handle much higher voltages and temperatures than traditional silicon.
That is fascinating. It is like a technological full circle. I want to touch on the practical side for a moment. Daniel mentioned that for most people, this is out of the realm of consumer preparedness. But if someone is listening and they are thinking about their own tech, is there any truth to the idea of a homemade Faraday cage? Like, if I put my laptop in a microwave or a metal box, does that actually do anything? Or is that just prepper folklore?
It is a common question. A microwave is actually designed to keep electromagnetic energy in, so it does work reasonably well as a Faraday cage in reverse. A heavy metal box with a tight-fitting lid can also provide some protection. But the problem is the seams, just like with the military bunkers. For a homemade solution to work, you really need to wrap your device in several layers of conductive material, like aluminum foil, with insulating layers like plastic or paper in between. This is called nested shielding. And you have to make sure there are no gaps. If you do it right, you can get 60 or 70 decibels of protection, which might be enough to save your laptop from a distant hemp.
So it is possible, but it is not a guarantee. And of course, your laptop might survive, but if the internet is down and the power grid is gone, you just have a very expensive paperweight that can play offline games. You can play solitaire while the world ends.
Exactly. Individual preparedness for an EMP is more about having non-electronic backups. Paper maps, analog radios, manual tools. The government command and control centers have to worry about the high-tech stuff because they have to run a country. For the rest of us, the best defense is a bit more low-tech. Resilience is not just about shielding, it is about having a plan for when the shielding fails.
Let us go back to the communications chain. Daniel asked about protecting the entire chain. We have talked about the bunkers and the fiber optics. What about the people at the ends of those chains? The mobile units, the soldiers in the field, the emergency responders. How do you harden a radio that a person has to carry? You cannot wrap a soldier in a steel box.
That is a huge challenge. For tactical gear, the hardening happens at the component level. You use specialized shielding inside the radio casing, and you use components that are designed to handle higher voltages. You also use something called a transorb, which is a type of diode that can clamp a voltage spike extremely quickly. But there is always a trade-off between weight, cost, and protection. A fully EMP-hardened tactical radio is much heavier and much more expensive than a standard one. Most military gear has some level of protection, but it is not at the same level as a fixed facility. The strategy there is often to have spare equipment stored in hardened containers, like a Faraday trunk in the back of a Humvee.
It is all about layers. Layers of shielding, layers of redundancy, layers of procedures. It is a very different way of thinking about technology. We usually think about tech in terms of features and speed. In this world, the most important feature is survival. It is about the minimum essential emergency communications network.
It really is. And I think that is what is so compelling about these military standards. They represent a massive collective effort to think through the unthinkable. When you read through Military Standard 188-125, you are seeing the results of decades of testing, often involving actual nuclear explosions back in the day, like the Starfish Prime test in 1962. We learned the hard way that a single blast in space could knock out streetlights in Hawaii 800 miles away.
It is a sobering thought. I mean, we are sitting here in Jerusalem, a city that is no stranger to conflict and contingency planning. It makes the discussion feel very immediate. When we talk about these systems, we are talking about the ultimate insurance policy for a civilization. It is the infrastructure of the end of the world.
It is. And as we move into an era where electronic warfare is becoming more common, like the examples Daniel mentioned with HPM weapons, these standards are becoming more relevant even outside of the nuclear context. If you can harden your infrastructure against a nuclear EMP, you are also hardening it against a lot of the tactical electronic weapons that are being developed today. It is a dual-use defense.
So, what are the big takeaways here? If we are looking at the state of EMP resistance in 2026, where do we stand? Are we safer than we were 10 years ago?
I think the main takeaway is that at the highest levels of government and military, the protection is very real and very sophisticated. The standards are robust and the engineering is proven. We know how to build things that can survive an EMP. The challenge is the scale. We cannot protect everything, so we have to make very difficult choices about what is critical and what is not. We are seeing a shift toward more resilient, decentralized networks, which is a good sign. But the civilian world remains the soft underbelly.
And for the average person, the takeaway is probably a mix of reassurance and reality. Reassurance that the command and control systems are likely to hold up, but reality that the civilian world is much more vulnerable. It highlights the importance of general resilience, not just for EMPs, but for any kind of large-scale disruption.
Exactly. Whether it is an EMP, a massive cyber attack, or a natural disaster, the principles of hardening and redundancy are the same. The more we understand the technical vulnerabilities of our world, the better we can prepare for the moments when those systems fail. It is about being informed, not being afraid.
I think that is a really important point. This is not just about a specific threat. It is about understanding the fragility of the systems we rely on every day. One thing that struck me in Daniel's prompt was the mention of the entire communications chain. We have touched on this, but I want to dig a bit deeper into the idea of the human element in that chain. You can have the best hardened radio in the world, but if the operator does not know how to use it in a high-stress, high-interference environment, the chain is still broken.
That is a vital point. Training is a huge part of the military standard requirements, though it is often in the accompanying procedural documents rather than the hardware specs. Operators are trained to recognize the signs of electronic interference and to use alternative methods of communication. This includes things like brevity codes, signal authentication, and even using manual relay techniques if the automated systems are struggling. In a post-EMP world, the person who knows how to use a signal mirror or a manual telegraph might be the most important person in the chain.
It reminds me of the old saying that the most important 6 inches on the battlefield are the 6 inches between your ears. No amount of steel shielding can replace a well-trained and adaptable human being.
Exactly. And in a post-EMP environment, that human adaptability would be the most valuable resource we have. The hardware provides the platform, but the humans provide the resilience. We are seeing more emphasis on analog fallbacks in military training now, teaching pilots to navigate by the stars and radio operators to use Morse code. It is about not letting the technology become a single point of failure.
I also want to circle back to the discombobulator and the high-power microwave weapons. Is there a danger that as these tactical weapons become more common, we might see them used in civilian contexts, like against protesters or in urban policing? If you can disable everyone's phone in a 3-block radius, that is a powerful tool for control.
It is a concern that many civil liberties groups have raised. There have already been reports of acoustic weapons and other non-lethal directed energy devices being used. A portable microwave weapon that could disable the phones and cameras of everyone in a square is technically feasible. It would be a very effective way to control a crowd without physical violence. But the implications for the right to protest and record the actions of the state are obviously huge. It is the dark side of the discombobulator technology.
It adds another layer to the discussion. It is not just about surviving a war. It is about how these technologies might change the nature of power and control in our daily lives. The same tech that protects a bunker can be used to silence a street.
Precisely. The line between a military standard for protecting a bunker and a tactical tool for controlling a population is thinner than we might like to think. It is all about how you apply the physics.
Well, Herman, I think we have covered a lot of ground today. We went from the nanoseconds of an E1 pulse to the microscopic vacuum tubes of the future. We looked at the steel boxes of military standard 188-125 and the non-conductive bridges of fiber optics.
It has been a deep dive for sure, and I think it is important to remember that while the topic can feel overwhelming, the engineering behind it is actually quite beautiful in its own way. It is about finding elegant solutions to some of the most extreme problems imaginable. It is human ingenuity at its most offensive.
I agree. There is a certain grim beauty in the logic of survival. I want to thank Daniel for sending in this prompt. It really pushed us to look at a topic that is often misunderstood or relegated to the fringes. It is a core part of how our modern world prepares for the worst.
Yes, thank you, Daniel. It is a perfect example of the kind of deep technical exploration we love to do on this show. It is about peeling back the layers of the world we take for granted.
And to our listeners, thank you for joining us on this journey. If you are enjoying my weird prompts, we would really appreciate it if you could leave us a review on your favorite podcast app. It really helps other people find the show and allows us to keep doing these deep dives into the weird and the technical.
It really does make a difference. We love hearing from you and seeing the community grow. Your feedback keeps us digging.
You can find us on Spotify, Apple Podcasts, and wherever you listen to your favorite shows. You can also visit our website at myweirdprompts.com for our full episode archive and a contact form if you want to get in touch.
And if you have your own weird prompts or questions you want us to explore, you can reach the show directly at show@myweirdprompts.com. We are always looking for new topics to dig into, no matter how niche or complex they might be.
Well, that is it for today. From our home in Jerusalem, I am Korn.
And I am Herman Poppleberry.
Thanks for listening to my weird prompts. We will see you next time.
Goodbye, everyone. Stay resilient.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.